Last time, we built the mathematical models, and right now, we are jumping straight into the payoff. Look, if you want to calculate the exact fault currents for any unsymmetrical fault on a power grid, the entire trick comes down to exactly how you connect your sequence networks at the fault point. Get that connection pattern right, and suddenly, the massive, highly destructive, real-world physics of a grid fault distilled down into, well, just some simple algebra. Let's get into it.
Just to quickly ground ourselves here, remember those three independent sequence networks we built in part 1 of this explainer? We've got the positive sequence network, we'll call that Z1, which represents your normal balanced operation. Then we have the negative sequence network, Z2, for unbalanced conditions. And finally, the zero sequence network, 0, 0, which handles the ground return currents. I want you to just think of these as three separate modular boxes of impedance. How we wire these boxes together literally dictates what kind of fault we're simulating.
Okay, let's dive right into this. The most common fault on any power system is the single line to ground fault, or LG. To mathematically represent this, you take all three of our boxes, Z1, Z2, and Z0, and you just connect them in a single series loop. Since they're in series, the exact same current flows through all three networks. That means the fault current simply equals the pre-fault voltage divided by the sum of Z1, Z2, and Z0. Now notice something really important here. The zero sequence impedance sits squarely in this loop. That means your grounding impedance directly limits the total LG fault current. And you know, this is exactly why power engineers deliberately add neutral grounding resistors to a system. By physically increasing Z0, they can actually mathematically and physically control the magnitude of that fault current to protect the equipment. Pretty clever, right? And this brilliantly illustrates the contrast when we look at a line-to-line or LL fault. Notice that for this fault type, you only connect the positive and negative sequence boxes, Z1 and Z2, in parallel. The zero sequence box, it stays entirely disconnected. Why? Well, because the line-to-line fault doesn't involve the ground at all. Since there's no path to ground, zero sequence current literally cannot flow. Because we've removed Z0 from the equation entirely, the current is just the voltage divided by Z1 plus C2. This generally produces a lower fault current than a three-phase or an LG fault at that exact same location.
Now, let's escalate things to the double line to ground fault, or LLG. This is where two faces are shorted together and touching the ground. To calculate this one, we use a series parallel connection. The positive sequence network, Z1, connects in series with the parallel combination of Z2 and Z0. Now, this interconnection is definitely the most mathematically complex of the three, and physically, it is absolutely brutal. Because the negative and zero sequence networks are in parallel, their combined equivalent impedance drops. Therefore, an LLG fault typically produces the highest fault current of any unbalanced fault type. Seriously, sometimes it even exceeds a dead short three-phase fault depending on the specific system impedances you're dealing with.
So, let's pull all of this together into a bit of a master key. If you memorize this pattern recognition rule, you really don't need to memorize complex IEEE equations. The interconnection pattern literally equals the fault type. Three-phase is just Z1, LG is all three in series, LL is Z1 and Z2 in parallel, and LLG is Z1 in series with Z2 and Z0 in parallel. It's really that simple. Every single digital protection relay setting in the industry depends entirely on getting these interconnections right so the relay knows exactly what specific fault signature to look for.
Now, what's really interesting is what happens when we transition from pure math to real-world physics. In the real world, according to IEEE Standard 80, faults are not just perfectly symmetrical alternating sine waves. When a fault strikes, the sudden change in the system's inductance creates an initial asymmetrical current wave with a decaying DC component. Basically, this means the immediate instantaneous current is much higher than our standard symmetrical equations predict. Engineers have to account for this initial massive spike using what's called the decrement factor to figure out the effective RMS value of the fault over its duration. If you ignore this DC offset, your switchgear might literally blow apart before the breaker even has time to open. No joke.
Furthermore, when that massive ground fault current hits a substation, not all of it goes straight into the dirt. IEEE guidelines require us to calculate the current division factor, or SF. This is the ratio of the total symmetrical fault current that actually flows between the substation grounding grid and the surrounding earth. You see, a significant portion of the fault current actually returns directly to the source by traveling back along overhead shield wires, neutral conductors, or underground cable sheaths. Finding the true amount of current entering the earth is absolutely crucial for sizing the grid conductors so they don't melt, and for ensuring the ground potential rise doesn't reach lethal levels for operators walking around the station.
Let's pause for a second and apply this directly. I want you to think about this scenario for a minute. A relay engineer needs to verify the sensitivity of a ground fault protection scheme. This specifically requires the zero-sequence network to be highly active to really test the relay's limits. So, out of the fault types we've discussed today, line-to-line, single line-to-ground, or balanced three-phase, which one strictly requires the zero-sequence network, making it the perfect basis for this study?
If you guessed single line to ground, you are spot on. LG faults are the industry standard basis for these studies because it is the only common fault where the zero-sequence network is mathematically and physically guaranteed to be active and dominant. Think about it. A three-phase fault has no zero sequence. An LL fault has no zero sequence. You absolutely must use the series interconnection of the LG fault to properly simulate and coordinate your ground relays.
So the crucial takeaway here is this. What started as abstract sequence boxes on a whiteboard is actually the literal blueprint of power system safety. Mastering these three interconnections, series for LG, parallel for LL, and series parallel for LLG, provides the absolute mathematical foundation required for every single protection relay setting across the entire global power grid. Without this, we're just guessing. But with it, we can predict exact currents down to the amp.
Which leads us to our final thought for this explainer. Now that you can calculate the exact current of any unbalanced fault, including the real-world DC offsets and current division factors, how do we physically stop it? How do we take these mathematical limits and actually program them into modern, digital IEC 16850 process bus relays? How do these optical sensors and massive physical circuit breakers communicate in mere milliseconds to clear these surges before they melt down the grid? Well, that is exactly what we're going to tackle next time.